Okay. So in an example yesterday, we had a differential equation and we were given two different solutions to that differential equation. We checked them both and they both worked. So that's definitely a characteristic of differential equations, is that there isn't just one solution. There are multiple solutions. The solutions, like we said yesterday, are equations, right? The solution to a differential equation is another equation without any derivatives in it. That makes the differential equation true that you can plug back in. So one of the ways to visualize what's going on with the differential equation is to make what we call a slope field. What I have here in this very first example is the simplest equation you could think of, dy dx equals y. What that means is that for any point, for any value of x and y in your relationship, you can find the slope of the tangent line, and it is just the y coordinate. So that's what's going on in this slope field. Everywhere where the y coordinate is 1, the slope of that line is 1. The higher your y coordinate goes, the steeper your line gets. When you go into negative y coordinates, your lines go down. When you make a slope field, whether it's computer generated or kind of hand drawn, you kind of have to decide how spaced apart you want your lines. This is not it is what it is. These lines are spaced a little bit less than a half of a unit apart for whatever reason. So you don't actually see the slope lines of one, but that's something you can do if you've got a program making them. You can bring them closer together. You can spread them farther apart. And obviously you can't put a slope at every single point on the graph, so you kind of just have to break it up. So that's what's going on there. And when we start looking at these, once we do one for ourselves, we'll see how these relate to the actual solutions. But the idea is, once you have the slope field, if you have any point on your solution curve, which would be your particular solution's curve, then you can kind of follow the slope field and sketch what that solution should look like. But as far as coming down to it, making one of these used to be pretty common. I don't want to say there was one every year, but it used to be a pretty common question for them to ask you to make a slope field on an FRQ question. From everything that I've seen, nothing official from College Board, nobody thinks that's going to happen this year because it's online and you've got a blank book. So possibly in the future, when you guys are gone and I've got new students, they may have something where students actually have to graph these things on the computer. I don't know what they're going to come up with. But for now, you wouldn't actually have to do one of these, although it used to be a common thing. More of the questions end up being matching questions. We'll see that in a minute. So the first differential equation we have is dy dx equals x times y. We make a slope field by basically taking a look at all of those points, taking a look at those coordinates, and doing xy, multiplying the x coordinate by the y coordinate. One of the ways that I like to do this, just for organization purposes, I kind of like to go down the columns and I like to write the numbers in and then draw the slopes. So as I go down these points and I do x times y, get this is in a straight line drawing thing, and I do x times y, basically what I get is -4, -2, 0, 2, 4 from multiplying the x by the y. Make sense? Yeah, okay. And one of the things about a slope field, honestly, once you get a number bigger than like 2, it's kind of really hard to determine the difference between a slope of 4 and a slope of 5. Those are pretty steep lines whenever you're dealing with whole numbers. Some of them on this graph, though, we can kind of visualize better. -4 means go down 4 and over 1. So I'm pointing that down 1, 2, 3, 1, 2, 3, 4 over 1. My little slope line should be pointing towards that dot down there. So the next one is down 2 over 1. So that should be pointing towards this dot here. It doesn't usually always work out this nice. And my slope here is 0, so I'll draw a horizontal line. And then I just have the positive positive slope, so I'm pointing just upwards at those same two dots, but looking up instead. Cool. So now I'll go ahead and erase my numbers. And I'll just do it again for the next set. Here we're going to have -2, -1. So everything's just going to be multiplied by -1. So it'll be -2, -1, 0, 1, 2. And again, I can do this one by just kind of pointing dots. So this one should go down 2 over 1. This should go to the origin. This one should also go to the origin. This one is horizontal. This one should point to the origin, and this one should point to the origin. On the next one, my x-coordinate is 0. So without writing the numbers, I'm going to write 0. I'm just going to do horizontal slopes. And really, this one's going to have some symmetry to it, because what you'll notice is we'll do 2, 1, 0, -1, -2. And those are really the same things we did on the other side of the line. So these ones are all going to point to the origin. And then the last set's going to mirror the first set. So without drawing the numbers, I'm going to have a -4, a -2, a 0, 2, and a 4. And there we go. We've got a slope field. Okay, so to kind of connect to what this is going to look like, I have something set up in Desmos here. So I had Desmos make the slope field, which was not something it does natively. I didn't have it. I'm pretty sure I found this and just adjusted it. But you should see that we have some similarities there. These are actually graphed at the same points. So you see your slope of -1 here. You see your slope of 2 here. So these literally do represent all of the lines that we just have. And using some stuff that we'll learn in the future, I found what we call the general solution, not the vocab word yet, but basically an equation with a variable that's kind of acting like a parameter. So it's not a variable like x that we change. If we want a particular solution, this a has one and only one value. But that's what a general solution is. But that is the general solution for our differential equation. So if I graph it, you'll see that the solutions do follow the curve pretty well. Or the curve follows the slope fields. So you can really see, the slope field here, if that curve was just a little wider, would be going in that direction. But you could see that it does feel like it matches the slope field. Okay. And I can adjust it. If I adjust, like I said, that parameter, I move the slope field. So in that, the higher it gets, the higher up my curve goes. And if I make my a negative, it slides to be down underneath the y-axis. There's a pretty generic solution to this differential equation. Just 0, y equals 0 would be a solution, but that's a pretty boring solution. And the other thing about this one is you really need to get really, really small zeros to get this thing to be wide. So if you put a really, really tiny 0 in, you can get it to shoot out to these, a really, really tiny a value, you can get it to shoot out to those spots. But you can see that when it does come close to a line on the graph, it does pretty well match that slope. The further away you get from the x-axis, the pretty steep those lines get. So you can see from the slope field that they're really steep. Make sense? Get the idea of that? Cool. All right, let's take a look at the next example. You guys do that one. In each case, you have to do y minus 2x. You may not have some of the advantages of being able to actually just point to another dot like we did on this one. But like I said, this is how steep a line with a slope of 4 is. If you tried to do a line with a slope of 5, which would just kind of go down to like where was I going? I was going to this dot, 1 dot down. You'll find that there isn't much of a difference in that little line that you're drawing. All right, so that is what your slope field should look like. By the time you got to the end there, the x equals 2 values, those slopes are so steep, -5, -6, that you're almost drawing a straight up and down little line there. Let's do the same thing. This one's a little bit more interesting. We'll take a look at it in Desmos. We can see some things moving on. So that was y minus 2x, y minus 2x. So all that work to draw the slope field when Desmos can just do it for you. Oh, I didn't realize I hit 3. Thank you. And again, using things that we would learn later on, or possibly not. I'm not sure if this is one that we could solve in Calc 1, but that is the solution, a particular solution. And as I move that b value around, that curve moves on the screen. So you can kind of see there were those zeros. So wherever those zeros are, that's where your curve is going to start to decrease instead of increase. So depending on where your starting value is, your curve will shoot up and hit one of those 0 values and then keep going. I think there's a spot. There shouldn't be a spot. I don't know if there's a spot where it, yeah. At some point, the curve can grow so much that it actually will never hit one of those and turn into a curve that just goes straight up. So working with these differential equations is different than just the integrating that we did, because our solutions to an integral were all vertical shifts of each other. But once you put a differential equation that's in terms of both y's and x's, changing that value that you get from integration, and that's really what these a's and b's are here. These are kind of equivalent to that c that we get when we integrate. Changing those does more than just horizontally shift your curve. So this curve does have some different things going on with it based on what that b value is. And once that b value gets high enough, it just breaks free of ever hitting that horizontal tangent line. Okay, so let's do one more example. So here is a dy dx that literally is something that we can integrate just to solve. So we will first sketch our solution, and we should see that our solution does match what we'll get when we integrate. So they want us to sketch a solution through the point 0, 1. So I'm going to go to the point 0, 1 with a pen. And I'm literally just going to follow what's happening here in this slope field. Going off to the right, this curve is leveling out. And coming over to the left, what you'll notice here is you kind of have these opposing lines there. That's usually a good indication that you have an asymptote going on. Because if you tried to get your curve to stop going down and start going up abruptly between those, it wouldn't make much sense. So basically, that's what your curve looks like. So we can solve this differential equation because it literally is just something we can integrate. We can change this into the integral of dy equals the integral of 1 over x plus 2 dx. Again, just shifting that dx over to the right-hand side because we're talking in the language of integrals, not the language of derivatives. And we end up with y equals everybody's favorite function, ln of x plus 2, yeah. Let's see. Yep. And that is exactly what we have. That's the ln function, but shifted to the left. But now here's something that's kind of important. We're actually not done. We do have to find that c value. So we'll deal with that in a second. But we are going to, this is something that does happen when we're in differential equations. The absolute value of ln x plus 2 is not a continuous function. There is a discontinuity because this is that's a terrible drawing of it, but this is what the absolute value of ln of x plus 2 looks like. But whenever you have a discontinuity in your function, we're never going to include that in our solution. Because this function, it's not going to be able to, if this was modeling something in the real world, there'd never be a way for a value on this to jump over to the other side. So we are going to lose those absolute value bars. The right-hand side is ln of positive x plus 2. This left-hand side is the ln of negative 1 times the quantity x plus 2. So we'll talk about this in a couple other spots as well, but this is just kind of like an introduction. So we are going to lose the absolute value bars. We're going to drop that off of our function, and we do need to solve for c. So we will plug in our 0 and our 1. So we get y, I'm going to put parentheses there. Oh, not y, we get 1 equals ln of 2 plus c, which means that c equals 1 minus ln 2. So that curve is actually ln of x plus 2 plus 1 minus ln 2. Okay, so example 4. Not that you would have this large of a match on the actual AP test, but one of the things they might do is give you a differential equation and ask you to match the slope field. So let's kind of look at this and see if there's any of these. We're going to write down some strategies on the next page. Anything that jumps out at you about any of these slope fields that we may be able to use to match, which one of those is produced by those different things? Yeah. What's that? D is sine. Sine y plus x. I think that is cosine, yeah. Because, and I'll tell you, this will be one of the things that we look at. The reason that I know this is not sine y plus x, because the sine of 0 plus 0, so this is the origin, is 0, and look at that origin there. We get 1. So one of the things we can do is we can sort of eliminate answers by looking at kind of easy to spot things. There's another thing we'll talk about. This is in both terms of y and x. If your differential equation is in terms of both y and x, then you should see a change as you go left and right, as well as when you go up and down. So if you just go straight up and down, do you see any changes? No. That is telling you that there is only going to be x on the right-hand side for letter D, and that's what letter D is. Letter D is cosine x. It doesn't matter what the y value is. That line has a slope of cosine x. All right, so we got 1 down. There we go. Gee, that's another important thing, is thinking about the domains of what we can put on the left. Letter G doesn't have any slopes to the left of some negative x value. And we're looking at that going to be, which one? G is going to be, yeah, root x plus 2. If you plug a number smaller than 2 into that, you're not going to get a result. So domains are definitely something we can look at. And with that, we should be able to get another one marked down. I don't know. That's what I was thinking about. So we got, is A number 5? Yeah, A is not number 5 for the reason that I was talking about. So Jack said A is number 7. I think I agree with that, because if x or y is 0, then dy dx is 0, right? And A definitely shows that. We don't have it, you can't see them, but you can definitely see the zeros all on the y-axis, and we can assume that that's what's happening on the x-axis because there's nothing being shown up and down there. Another thing we can look at, negative xy. This one's going to go by quadrants. So in the first quadrant, are my slopes positive or negative? Those slopes are negative. If I plug two positive numbers into negative xy, am I going to get a negative? Sure thing. And the bigger those x and y get are, the steeper my slopes are. So that will work in all four quadrants. In quadrant 2, you've got one negative and one positive. Negative xy is going to give you a positive there. So yeah, I agree that 7 is A. I think so. Yeah, 5 is H because you can't put a negative value into ln. So, and the ln of 1 is 0. So yeah, so for both of those parts. All right. Is E3 sine y plus x? Yes, I think so. I think E is 3. Here's why C isn't 3. It doesn't change up and down. So this is going to be purely in terms of x's. So C has got to be something that's only involving x's. I see it. Yes. C is 2. So this is going to go to, when you get big x's in, this is going to go to 0. Because you're raising e to the negative 2.2x squared. So if you start putting big x's in there, yeah, great, you're multiplying by that big x, but you're also multiplying by e to a bigger negative power at some point. So yeah, so that's why that one is going down to 0. All right, so what do we cross out? If I cross all the things out we've used, we did C and A, I missed, yeah. So we only have B, E, and F. Yeah, we talked about E being 3. Yeah. And the thing about this is the bigger the x's get, sine y is capped at 1 and negative 1. So the bigger the x values that you put in, the steeper your slopes are going to be. So by the time you get over to that end of that graph and you're putting, whole numbers in, maybe that's, I don't know, there's no scales here. Maybe that's 5, maybe that's 10, but you're getting slopes of 5 and 10. And you can sort of see how this thing's sign is affected, especially in the middle, by the y terms. So letter E is going to be that one. Yeah. B is 8. Yeah, cosine x plus y, that's a weird one. That causes the cosine graph to sort of just kind of be diagonally. That is B. And that means that the only one we haven't listed is F. But F doesn't change horizontally, right? F only changes vertically, which makes sense because it's fully in terms of y squared plus 1. Okay. All right. Tricky. I mean, just jump right in on them with that one. Strategies for slope fields. Things that you can do. Set x equal to 0 and look at the y-axis. Set y equal to 0 and look at the x-axis. What's happening when you do that? Because that should then be mirrored on those axes. And then kind of to piggyback off that one, if dy dx is only in terms of x, then your changes are only going to be up and down. And if dy dx is only in terms of x, then your change is only going to be left to right. Only in terms of x and only in terms of y. Only terms of y, only terms of x. I added into that one, but if you can easily tell when dy dx is going to be greater than 0 or less than 0, because obviously if dy dx is greater than 0, you've got to see positive slopes. That's how we did the negative xy one. And if dy dx is less than 0, we should only have negative slopes. Again, it's just kind of looking at your function and trying to decide, okay, can I easily see when this is going to happen? And then, of course, kind of to piggyback around on that one, when dy dx equals 0, we're horizontal. And when dy dx is undefined, we're vertical. So looking at the sign versus just straight up 0 or 0 denominator. And then the last one that we kind of used was end behavior. And this was the one with that e to the x squared thing. Actually, it was two of them. It was the one with the e to the negative x squared, because that was going to go to 0. It was also the one that was the sine y plus x. As you got big x's, those slopes were just going to keep going up and up and up. The sine y wasn't going to do much to the large x value. Right.